we have to remember for 6.4, we have to remember all about the binomial distribution, which we did in Chapter 5. So I'm going to revisit that a little bit. We're going to talk about what a binomial distribution is and a binomial experiment is, and how we can use the knowledge that we already have about binomial experiments and distributions and how they can be related to the normal distribution. Essentially what we're going to do, if certain conditions are met, we can use the normal distribution to find the binomial distribution. That's why it's called an approximation. And it's when we do the approximation and when we do the upper and lower bounds, that's when it turns into an approximation. So let's revisit binomial distribution. Okay, we can use a binomial distribution, or we have a binomial experiment when the following things are true. Okay, and this is just from 5.3, I want to say. So you can write it down again if you want, and I'll go through it real quick here in a sec. Okay, so in order to be a binomial experiment and consequently a binomial distribution, we have to meet all these conditions. Each trial can only have two outcomes, a success or failure, and the problem will dictate whether it's a success or a failure. But there's only two possible outcomes. You have to have a fixed number of trials. The outcomes are independent of each other, so they don't affect each other, and then the probability of success always remains the same. And that has to do with the independence piece. Okay, so that's just reviewing what that is. Now, when we looked at this, there was, if you remember, N, P, Q, and X. Okay, that's what this is. So if you recall, X was the number of successes, N was the number of trials, P was the probability of success, and Q was the probability of failure. And we had this formula that we used in order to calculate the probability. And we could also find the mean, we could also find the variance, and we could also find the standard deviation when we had these numbers. Okay? And we're going to revisit that a little bit today. But really I want to talk about the conditions that have to exist in order to use the normal distribution to approximate the binomial distribution. And here are the conditions. So this is important because you're going to have to demonstrate this before you can actually go on and do the problem and verify that this is the case. So if NP is greater than or equal to 5 and NQ is greater than or equal to 5, then you can use the normal distribution to approximate. So you're going to have to show that both of these are true. Okay? That they're both greater than or equal to 5. If they are not, the sample is not big enough, the distribution is not big enough to use it as an approximation. Okay? Oftentimes it has to do with the number of trials. The more trials that we have, the closer it will get to looking like a normal distribution. So this is why we have to do this test. Keep in mind the probability is always between 0 and 1. So oftentimes we want to make sure that the trials are well over 10. If we only have a few trials, this is probably not going to work out. Okay? So the more trials, the better. The more trials, the closer it is to the normal distribution. And then the next piece is you have to check for this. So just as I've said, you just have to check for it and show it. So show what NP is, show what NQ is, so that you've proven that you can move forward. So if this doesn't happen, if these aren't both true, then you can't use the normal distribution. You have to go back to Chapter 5 and use the formula for finding probability from the binomial distribution. You can't use it as an approximation. And that one has a combination, P, I think it was like P to the, I'm not remembering right now. It's like P to the n minus x and Q to the x or something. I don't remember what it is off the top of my head. But for the most part, this is going to work out in these problems that we're working on today. Now, that's the first piece that's tricky. The second piece that's tricky is coming up with the upper and lower bounds, because what we're trying to do is punch this in the calculator. Normal CDF, find the bounds. We need to calculate, we're going to have to calculate the mean, and you're going to have to calculate the standard deviation. That's what we're trying to do, is still be able to punch it in our calculator. But we have a bunch of steps that we have to take in order to, before we can do that. Okay, so I'm going to show you this chart, but I also think I've got a better way than just memorizing the chart. Okay. So, and this chart has to do with the correction for continuity. Okay, since it's an approximation, we have to make a correction. We have to accommodate our bounds, make our bounds accommodate the actual problem. Okay, and what this all is about is talking about the upper and lower bounds for when we enter it into the calculator. And so this correction, I'm going to put this chart up here, and you can take a picture of it, and I'm going to sort of explain it, but I'm going to give you a better way to remember it, I think, than what I'm going to show you. But what I'm going to show you is straight from the book. And it looks like this. And if you want to grab it from your book, it's on page 342. One thing I will say that you need to remember are these two things here. If you recall, when we found standard deviation and when we found the mean, you're going to need to be able to find the mean and the standard deviation using N, P, and Q again. And you're going to actually have to do that. Once you get this kind of situated in your notes, I'll go through what all this is saying. One of the things I will tell you is that the book doesn't really show you how to use the calculator to do this. It converts everything to z values, and we're not doing that. Our calculator will do it all for us. So what's important is what we're really doing here is finding the bounds, calculating the mean, and calculating the standard deviation. Those are the four things that we're going to do here in order to find these probabilities. Now, when we're looking for a probability of something equal, see again, we're not finding the straight probability. We're using the normal distribution to approximate it. And so when we can't just say x equals and then plug it in and, table E, that doesn't work like that. We have to create some boundaries that encompass the value that we're trying to find. And we do that by using boundaries back from the early part of the chapter, or the book, the unit, the school year. So when we're looking for a probability of x equals a value, the bounds are pretty easy. So when I'm looking for that exact value, I subtract half of a point and I add half of a value. So if this was an 8, it'd be 7.5 to 8.5, and that's my upper and lower bound. Okay? When it equals a value, that's easy. It ensures that this value is contained within these boundaries. Okay? And if you remember how to do boundaries, when it's an integer, you add or subtract the next sort of half a decimal point. And that was something we did back earlier in the year. All right. Now, this part down here, you can remember all these and memorize these four things, and that is certainly one way that you can do it. I don't recommend it. I would rather you think about what's being said here, and you can then picture how to create the boundaries so that the values are contained in them. Okay? Now here's what I mean. So for example, on this first one, x is greater than or equal to a, which means a is part of the boundaries. A has to be included. So what we then do is we go down a half a tick, because everything greater than that, because think about how our boundaries are set up. It's a less than, it's a greater than, or it's in between. And this is the in between. I ensure that this value a is in between these two numbers. Here, since a is included, I go down a half a tick because everything greater than that will also include that value of A. Okay? But for this one, A is not included. It's greater than A. So I go a half a tick beyond that. And again, it's all an approximation. That's why we only go a half a value. Okay, same with this one. Since it's less than or equal to A, I want A to be part of the answer. So I move the needle sort of bigger than it so that everything less than that also includes A. And then same with down here. A is not included. So I go the needle, I move the needle to the left of A, which is making it smaller, because then A won't be included. It'll make more sense when we look at an actual problem with numbers, and hopefully it'll make more sense anyway. So let's do that. There again, we need the mean and the standard deviation. I already talked about that. All right, so let's talk about, because one of the big problems, computing the mean and the standard deviation is easy. It's just the formulas. NP is the mean, the square root of n times p times q is the standard deviation. That part's easy. Creating the boundaries, that's the part that I think you're going to find challenging, and that's what that table was all for. Okay, so we're going to go through a situation. Now, in your problems, you're not going to find all 5. You'll be given one of them for the problem, and you'll have to create the boundaries. I'm going to go through all 5 so that we have all scenarios covered. And that way, regardless of what one you encounter, hopefully you'll understand how to do that. Okay? So when it's equals, it's easy. Okay? You just go a half a tick below, a half a tick above, and those are your boundaries. So my lower boundary here is going to be what? 6.5, and my upper boundary is going to be 7.5. If you just add and subtract a half a point. Okay? So for the lower and upper bounds, I would put 6.5 in, and I'd put 7.5 in the calculator, and then you will have had to calculate the mean and the standard deviation, and then you plug it in and you're done. Okay? For the equals one, it's easy. There's a little more thought involved with the greater than or equal to, the less than or equal to. Not a ton of extra thought, but there's some thought. Okay? And everything that we're writing over here is what you use for the calculator, what we've done before, with the -1 e to the 99 or 1 e to the 99. Okay? This one is the only case where I'm going to have a number on each end. The rest of these are going to have either a 1 e to the 99 or a -1. Okay? So let's go through one at a time. So when I'm looking for the probability that x is greater than 7, is 7 a part of that? Yes. No. One of those. No. Greater than 7. Can 7 be part of that? No. Greater than 7. Not equal to 7. Greater than 7. So think about the values that are greater than 7. And again, you're always adding a half of a point. So if I want to exclude 7, pick a number bigger than 7 and beyond, what should I pick? 7.5. Okay? So in this case, what I do is I exclude 7, and so everything greater than 7.5 will actually have this value. Again, it's an approximation, so that's why it's not exact. But if I used 7 instead of 7.5, I would be including 7. And we don't want to include 7. And it's always a half a decimal value. Okay?
Wait, so what would the lower and upper bounds?
So what is the lower bound here?
7.
7.5 is the lower bound. What's the upper bound?
Infinity.
Yeah, it's infinity. 1 e to the 99. So this is the same as what we did before now. Once we do this setup over here, then we enter it in our calculator just the way we did the other problems. Now in this case, in the third one, 7 is included because it's or equal to. So I need to figure out a way to find a value. So again, it's always I'm either adding a half a point or I'm subtracting a half a point. So what's the value that I'm going to go to here? 6.5, because again, both of these I'm going to have a greater than sign. It's just figuring out which is it going to be 7.5 or 6.5. And since I want 7 to be included, I actually go down 1 because now 7 is included in this inequality. Okay? Remember that our bounds are always greater than or less than, not or equal to. But I have to manipulate it in such a way, because we're approximating, to include the value because of the or equals to. It's always adding a half a point or subtracting a half a point. Again, if you want to use the table that I showed you and just memorize them all and figure out which one is which, that's fine, you can do that. I prefer to think about it the way I'm sort of showing it to you. Okay? For this next one, less than 7, is 7 included? So I'm either going to have less than 6.5 or less than 7.5. Which one does not include 7? Less than 6.5. If I went less than 7.5, 7's in there. But there's no or equal to, so I have to exclude that 7. So I go down to 6.5. Okay? This inequality does not include 7. For this one, because of the or equal to, I want to include 7. So I'm going to go less than 0.5. Because 7 is included in this inequality. Okay? So notice a couple things to help you kind of keep this straight. The inequality symbols always point the same way as the actual problem. Okay? Except there's no or equal to. Notice these are both greater. This one happens to be or equal to. But they're both greater when I actually use my approximation to put it in the calculator. Okay? It's whether or not the value that's is being used here is included in my inequality. If it is, you have to write the inequality so that it is also included in it. If it is not, then you have to exclude it with your half a value. Okay, does that make sense? Questions? All of this was just for the setup. Okay, let's go through an actual problem. So I found this problem in the book, Widowed Bowlers. So I took it on page 343. Seems like a...
Is that an actual statistic?
Apparently so. I don't know. Maybe I'll take a quick little poll in my bowling league Wednesday night to see how many people are widows or widowers. In this bowling league, 10% are widowed. So they're either their spouse has died at some point. Of 200 bowling league members, what's the probability that 10 or more will be widowed? Okay. So we're looking for the probability.
Say one.
Well, before we can even do this, we have to decide if we can use a binomial, a normal approximation. So we have to find NP, and we have to find NQ, and we have to show that those are both greater than or equal to 5. If they are, then we can proceed. And we need NP anyway, because NP is the mean. Okay? So in this case, what is N? 200. Those are the sort of trials. There's 200 people. P, in this case, is the probability that someone is widowed. That's the quote-unquote success. Okay? And then the failure would be someone is not widowed. So what percent do we expect them to not be widows? 90%.
Can we just say 20 people are widowed?
Okay. Well, good question, but we're not. There's only two outcomes: widowed or not widowed. So if you're not married, then you're not widowed either. All right. So we need to find NP, and so we already said N was 200, and P was 10%. Okay. So that's 200 times 1, which is 20. So that's greater than or equal to 5. So we keep going. So that's good. Okay. The probability of failure, 90% are not widowed. So that's going to be 200 times 0.9. So that's 180. So again, that is also greater than or equal to 5. So I can use a normal approximation. I have enough trials. I have enough of a probability when multiplied by those trials. So I've demonstrated that both NP is greater than or equal to 5 and NQ is greater than or equal to 5. So I can keep going now. All right? With this idea that we can use the normal distribution to approximate our probability. So that's what that says, okay?
What if they aren't 10, 5, or
If they aren't greater than or equal to 5, then you can't use the normal distribution to approximate. You have to use what we did in chapter 5 in order to find the probability, okay? But for the most part, in these problems, they're going to be greater than or equal to 5. Now, what probability am I actually looking for here? Okay, so I'm looking for the probability that 10 or more would be widowed. Let's put it into inequality context. What does this really mean? Is it greater than or equal to? 10 or more. So 10 is included.
Yes.
Okay, so I'm looking for the probability that x is greater than or equal to 10. Okay, and it's based off of this, 10 or more. If it just said more than 10, then it would just be greater than. 10 or more, 10 is included. So the next thing that I have to do is find the boundaries for this. So why don't you go ahead and try to find the boundaries for this?
So wait, you have to find all 5. No, never mind.
Yeah. So go ahead and try to find the boundaries for this the way we did on the other page, and let's see if you got the hang of it yet, even though it's your first time doing it. No.
X is greater than 9.5?
X greater than 9.5. Okay, so when I write the boundary, a couple things. One, it faces the same way. It will never have an or equals to. Okay? Now, I have to include 10. So if I have to include 10, I have to pick a value. When I pick that value, it's either 10.5 or 9.5. X greater than 10.5 does not include 10. So I have to go down, make sure that it's included. And then I still wrote it greater than or equal to. There we go. So greater than 9.5. Because greater than 9.5 includes 10. Greater than 10.5 does not include 10. So I need to have that. Because I messed up that or equal to on this, it's going to keep showing up on every slide after this, and I'm not going to fix it every time. But just know this is always supposed to be greater than, okay? Ignore the or equal to, because whenever I set these up, I copy, paste, copy, paste, copy, paste. So it's going to be there over and over again, and I will have to fix that eventually. All right, so so this is my boundary. So when I put this in the calculator, what am I going to put? What's my lower bound here? 9.5 is the lower bound. What's the upper bound? 1E99. So that's how I'm going to set that part up in the calculator. I still need the standard deviation and the mean. So when I find the mean, it's n times p. Well, we already found n times p. What was that? We already did that. Okay. Now I need to find the standard deviation. The standard deviation is the square root of n times p times q. So go ahead and do that. What is the standard deviation?
Wait, why is there 20 written?
Oh, no,
What is the standard deviation? Leave it in the square root. Square root of 18. Okay, so 20, because that's NP, times 0.9. So that's square root of 18. So now I have everything I need. I have my boundaries, I have my mean, I have my standard deviation. Normal CDF in the calculator, go ahead and do that. So here's what you should have entered into your calculator. Okay, just like that. How many entered that in? How many entered that in?
Me. Wait, hold on. Yeah?
That's all you should have done.
What's the answer?
Well, let's think about it. Let's think about what the answer should be before we actually answer it. Okay, they're saying that 10% are widowed. So what is 10% of 200? 20. So the probability that 10 or more should be high or low? should be really high, right? If 200, if 10% of 200 are widowed and they're wanting to know 10 or more, we already think 20 is what it should be. So it should be just about everything. 10 should be way the heck down there. Okay.
Yeah, but you also have the 180 that are not widowed, right?
Right, but we're asking for the probability of 10 or more. We think it's going to be 20. Okay? Since we think it's going to be 20, the probability of it being 10 or more should be really high. Because we expect it to be 20. 10 is low. Okay? How many had that? 99.33%. Okay? So, that's what this lesson is. Okay? Mostly it's figuring out how to set these bounds up, verifying that we can actually use the normal approximation. Okay? If we can't use the normal approximation because these values aren't greater than or equal to 5, then you have to go back to 5.3 and remember that. Or, in your calculator, now that we're in the distribution menu, there's actually a way to find the probability using a binomial distribution. And if you arrow down in their distribution menu, you'll see it. There's two of them. There's a binomial PDF and a binomial CDF. You can play with that if you want.